everybody, welcome back to Experimental Math. Today we have Mingjia who will be telling us about systematic counting of pattern avoiding partitions.
And some new partition identities.
I'm sorry.
Okay, so hi everybody. Thank you for coming to my talk. As Yuna mentioned, today I'm going to talk about systematic counting of pattern avoiding partitions and some new partition identities. This is joint work with Matthew Russell and Dr. Lee. Okay, so for those of you who are new to partitions, welcome to this exciting field. So this is simultaneously a field that's very accessible to even primary school students and its basic definitions and ideas, but also has wide range of connections to other fields of mathematics like the algebra and statistical mechanics and so on. So what is a partition? A partition of a positive integer n is a finite, non-increasing sequence of positive integers. Let's say we have k parts, lambda 1 to lambda k. Okay, so whose sum is equal to n. For example, 4421 is a partition of 11. So hopefully you all know about a little bit about the ordinary generating function of a sequence an. So it is a power series whose coefficients are the terms in the sequence lining up in order. That is a power series and goes from 1 to infinity. An Qn is a generating function for sequence an. For example, let an be the number of partitions of n into parts all equal to a positive integer I. Then the generating function for an is just 1 over 1 minus q to the I, which is 1 plus q to the I plus q to the 2i, and etc. So let's say we take I equals to 4. So we are partitioned integer n into parts all equal to 4. So we have 1 plus q to the 4 plus q to the 8, etc. So why do we not have q to the 5 term? Well, that's simply because we cannot partition 5 into parts all equal to 4. We can only partition integer that's a multiple of 4 into parts all equal to 4. All right. Okay, so before I introduce some well-known fascinating partition identities, let me introduce Q pocket heaven symbol. So A semicolon Qn is defined to be this product. So with n terms in n, 1 minus a to the a times q to the I, q to j goes from 0 to n minus 1. And a semicolon q infinity is taking n to infinity here. Okay, so probably the oldest partition identity is the oldest or distinct identity that's discovered proved in 1748. The identity states that if we partition the number of ways to partition integer into distinct parts is equal to the number of ways to partition that same integer into odd parts. So let's say we want to partition the integer 4. So that's 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. Okay, so...
and 4.
Yes, 4. So
and 4 itself, so we have 5.
did I say 4? Sorry. So, yeah, there are 5. So, Robert, how many ways are there to partition 4 into distinct parts?
We have 3 plus 1.
Yep.
And that's it? All of them repeat parts?
No, and 4.
Oh, and
4.
4.
Very good. All right. So how many ways to partition 4 into odd parts?
An odd number or parts themselves?
The parts are all odd.
Only 1. And then 2.
Yep. So this one and this one, right? 3 plus 1 and 1 plus 1 plus 1 plus 1, both of them. So the number of ways to partition 4 into odd parts, there are 2 of them. Partition into distinct parts, there are 2 of them. So that this applies to any integer n. So I think that's very fascinating. But it has also just one line generating function proof. It also has a bijective proof, which is not too hard, but I won't talk about it here. And now going to the more related topic of today's talk, Rogers-Riemannian identities. That's first discovered, proved by Rogers in 1994. So these are two identities of Rogers-Riemannian. The first identity says that the number of ways to partition an integer into adjacent part, such that adjacent parts differ by at least 2, is equal to the number of ways to partition that integer into parts that are 1 or 4 modified. And the second one says the number of ways to partition an integer into parts such that adjacent parts differ by at least 2, and in addition, the smallest part is at least 2. Is the same as the number of ways to partition that same integer into parts that are 2 or 3 modified. Okay. So a slight digression. So P of n is a partition function. So that counts a number of partitions of n. So I just think these three congruences are pretty fascinating. So I just want to show everyone who are new to partition identities here. Take any integer that's 4 mod 5 and count how many ways to partition that integer into any parts. Then the number of ways is divisible by 5. Right? And also we have P7k plus 5 is 0 mod 7, P11k plus 6 is 0 mod 11. But going back to the main sections of this talk is going to be separated into two parts, just 2 parts. The first part, we are going to talk about efficient algorithm for counting pattern avoiding partitions. Second part, we are going to talk about how we use this algorithm to actually search for new partition identities. Okay, so again, Pn is the number of partitions of n. Pnm is the number of partitions of n with largest part m. So the first one should be pretty easy to see. Pn is equal to summation of Pnm, and goes from 1 to n. The second one is also not too hard. So this is saying if we have a partition that the first part, the largest part is equal to m. After we chop off the largest part, what we're left with is a partition of integer n minus m. And let the second part be m prime. So, n prime can range from 1 to n. So how do we get this nice recurrence? We substitute nm for n minus 1, n minus 1, and have another equation like this, and then subtract this that equation with this original one to get this nice recurrence relation, which enables us to find an efficient way to compute a table for P of n, which is quadratic in time and memory. Now, what if we want to count not just any partition efficiently, but partitions with some restrictions? What if we want to count partitions with just adjacent parts differ by at least 2, like the Rogers-Riemannian? Okay, so for that we need to introduce some definitions. So a pattern is a list of non-negative integers. So here we don't restrict the order to be increasing or decreasing, just any list. So partition contains the pattern if there exist subpartitions such that the consecutive differences match the pattern. So for example, 7, 6, 5, 4, 4 contains the pattern 1, the pattern 0. So it contains the pattern 1 because 7 minus 6 equals to 1, 6 minus 5 equals to 1, or 5 minus 4 equals to 1. The pattern 0 because 4 minus 4 equals to 0. Pattern 1, 1. That corresponds to subpartition 7, 6, 5. The pattern 1, 0 that corresponds to 5, 4, 4, and so on. So a partition, so actually I would like to mention here that this kind of condition is already, like we didn't innovate this. This is already used by other people, and many times it's referred as difference conditions. But here, just for simplicity, I would like to use the term pattern instead. So a partition lambda avoids globally. We use avoids globally or avoids interchangeably. So a partition lambda avoids globally the pattern if it does not contain the pattern. Partition avoids the set of patterns A if it avoids every pattern in A. So for example, partitions whose adjacent parts differ by at least 2 is equivalent to partitions that avoid 0 and 1 globally. If you have any questions, feel free to ask. So a partition lambda contains a pattern at the beginning if we begin from the largest part of the partition and the pattern immediately appears. So for example, 76544 contains a pattern 11 at the very beginning. Okay, so now with these notations, I can introduce our initial algorithm. We say this initial because we're later going to generalize this. So I'm going to use a simple example to illustrate this algorithm. All right, so let P11 and n be the number of partitions of n with largest part m avoiding 111. P prime 111 and m is the number of partitions of n with largest part m avoiding pattern 111, and in addition avoiding the pattern 11 at the very beginning. And P double prime, also same global condition, but now avoiding 1 at the very beginning. Okay, so why do we have this first equation? So same idea, we start with a partition that avoid 111 globally and start the largest part being n. We chop off the largest part m. Let's say the second largest part is n prime. So we are left with a partition of n minus n, right? So if n prime is equal to n minus 1, so the resulting partition not only has to forbid 111 globally, it also has to forbid 11 at the very beginning. Because otherwise, if we add back the n, we will get a 111 pattern. So now if n prime is not equal to n minus 1, after we chop off the largest part m, we also only need to avoid 111 globally. There needs not to be any beginning restrictions. So that's why we have p prime here, but p here. Okay, so the second equation, p prime 111 and m is equal to this, these two guys, the sum of these two guys. So why is the same idea, right? So we start with a partition that avoid 111 globally and 11 at the very beginning. After we chop off m, then we are left with partition of n minus n. And depending on the m prime, if m prime is equal to n minus 1, then we are left with a partition not only avoid 111 globally, but also avoid the pattern 1 at the very beginning. So that's why we have this p double prime here. And if n prime is not equal to n minus 1, we only avoid 111 globally. So same idea for this one. So, all right. So this can be actually made into a quadratic time and memory algorithm to compute P111 of n. And actually for any finite set of patterns A, we can find the quadratic time and memory algorithm. So using the same idea, substitute n for n minus 1 and n minus 1 and do the subtraction. Okay. So going beyond, what if we want to count partitions with more specific restrictions? For example, not just globally, but also based on congruence conditions. So what do I mean by that? So consider one side of Schur's celebrated 1926 theorem, partitions of n into parts with minimal difference 3, and with no consecutive multiples of 3. Okay, and about a more complicated Kennedy-Russell conjecture, no parts repeat, adjacent parts do not differ by 1, if the smaller part is even, a subpartition of type 2j plus 4 plus 2j plus 2 plus 2j is not allowed. So here subpartition, when we say subpartition, we mean we are taking a subpartition from the original partition whose parts are consecutive. So for example, if the original partition is 76544, so 654 is a subpartition, but of 5 for this is not a subpartition. These parts are consecutive. Yeah?
So is disallowing a subpartition of this type, can you state that in the language of pattern avoidance?
Yeah.
Okay.
Yeah, so we're just going to talk about that, but since you asked, so this just means, right, so if the largest part of the subpartition is even, 2j plus 4 is just an even number, we are forbidding the pattern 2 immediately after that. Right, so if we take j, j can be any integer, so we take j to be 0, we're forbidding 4 2, and if we take j to be 1, we're forbidding 6 4 2. 6 plus 4 plus 2. Okay, and also, in addition, smallest part has to be at least 3. So we are not allowing 1 or 2 as part. Okay, so for that we need to refine our definition. Let M and A be the same as before. So A is set of patterns to avoid globally. So mod, loosely speaking, is the list of patterns to avoid according to mod conditions of the largest part of a subpartition. So it's best illustrated by an example. Okay, so let's say we are having this mod condition, which is a list that contains 3 sets. So this already gives us information that we are concerning mod 3. And the first set corresponds to 0 mod 3, the second corresponds to 1 mod 3, the third corresponds to 2 mod 3. So if we say a partition avoid mod or obeys this mod condition, we simply mean that if we take any part of the partition, let's say that's M, depending on the congruence classes, M falls into of mod 3, we want to forbid patterns immediately after M going to the right. So let's say M, in the first case, let's say M is 0 mod 3. Equivalently, let's say M is equal to 3j plus 3. So M falls into the first class, so there's only one pattern here, 1, 1. So that means we're avoiding the pattern of the subpartition of the type 3j plus 3 plus 3j plus 2 plus 3j plus 1. Any questions? Okay, so if M is 1 mod 3, so say M is 3j plus 4, then we are avoiding 3j plus 4 plus, so M falls into the second class, so it has only one pattern 2. So we are forbidding subpartition of the type 3j plus 4 plus 3j plus 2. So there's nothing in the third set. So if M is 2 mod 3, we forbid nothing. Okay, so we're only forbidding subpartition of type 3j, so these two types. Okay, how about this one? Anyone has the answer? So again, the first one corresponds to 0 mod 2. Right, so that means if the largest part is even, which is 2j, we are forbidding 2j plus 2j. So the largest part is odd, we are forbidding 2j plus 1 plus 2j plus 1 plus 2j plus 1. So even parts are not allowed to repeat, and odd parts can appear in most slices. That's what this notation means. Okay. So we also introduced the set of patterns to avoid at the very beginning. I, the set of subpartitions to avoid. We call this initial conditions. So usually I is just something small, like this. So if I is the set containing 1, here this 1 is a partition, not a pattern. So this means we are forbidding subpartition 1. In other words, we are forbidding 1 as a part. Sometimes when you look at this, we're forbidding, actually, this can never be the case because it's a partition, so only 2-1 is allowed. So we're forbidding 2-1 as a partition, subpartition. Okay, so let's look at these identities in light of the notation. So sure, parts with minimal difference 2, that's equivalent to A is equal to 0, 1, 2. No subpartition of type 3J plus 3 plus 3J that correspond to mod. So this is, we know it's concerning mod 3. So we have 3 things in this list. And within the largest part, if that's 0 mod 3, then we are forbidding the pattern 3 immediately afterwards. So we have a 3 there. So the Kennedy-Russell conjecture, no parts repeat. A is equal to the set containing 0. Subpartition of type 2J plus 1 plus 2J is not allowed. So as we mentioned before, the largest part is odd, then we're forbidding 1. So that's why we have 1 here. And all these 3, 4, and 5 correspond to the largest part being even. So they all falls into the first set. So this first one forbids 2, 2, 2, 1, and 1, 2. So we have these. Smallest part is at these 3. So I is equal to 0, 1, and 2. Okay, so now finally we can talk about our generalized algorithm. So let GP MNA mod BI be the number of partitions of N, which with largest part M and the restrictions A mod BI. So if M is greater than N, return 0. There's no partition with the largest part greater than the integer we are partitioning. If M is equal to 1, return 1. So N itself is the only partition. So second step, check if M is equal to the largest part of any of the forbidden subpartitions in I. If so, and if the forbidden subpartition is just M, then return 0. Right, so so if M is in I, right, so let's say M is equal to 4. Right, so this is not possible. We are forbidding 4 as a part. Right? So we return 0. Otherwise, we add the underlying partition pattern to the beginning restrictions. So let's say I is 4, 3, and M is equal to 4. So that means, okay, so this is our partition. We are forbidding 3 as the second part, right? So that means we are forbidding the pattern, the underlying pattern is 1. So we add that 1 to the beginning restrictions. So from that we obtain a new set of beginning restrictions, B prime. Okay. All right. So third step, this is onto the core idea of our algorithm. So, but you can see it's not all that different from before. So if mod is equal to the empty set, there's no mod restrictions, then by chopping off the largest part. So again, we chop off the largest part. So we get the following recurrence. So now this is M prime and minus M. So note that the valid M prime will be those such that the singleton M minus M prime it's not in the forbidden patterns, right? Because if they are, then we are not counting them, right? So either globally or at the beginning. B prime is a set of new beginning restrictions. B double prime is a set of new beginning restrictions obtained from A union B by talking of the difference n minus n prime from the patterns in A union B prime. So A union B prime is the forbidden patterns that we start with. But if, so as an example, if AB, little ab is in the set of forbidden patterns either globally or at the beginning, and after we chop off the Bm, let's say n minus n prime is equal to A, then we result in a partition that also needs to avoid B at the very beginning. Right? So that's why we add B to B double prime. Okay, good. So, right, very good. And then the fourth part, if mod is not equal to empty set, let the length of mod be k. If n falls into the ith congruence class, mod k, then we get the following recurrence. So since m is given, right, it's an input variable, so we already know which congruence class it falls into. So again, value n prime will be such that the m minus n prime is not in the forbidden patterns either globally or at the beginning or according to the mod condition. Right? Because if it is, then we're not counting these. And B double prime is a set of new beginning restrictions obtained from A union B prime union mod I plus 1. So the only difference from the third step is we have the mod I plus 1 because we also have mod restriction, and we know n falls into the ith congruence class. So still chop off the n minus n prime, and we get the set of new beginning patterns. So hopefully that is clear. So close analysis is still to be done, but I think this algorithm can also be made quadratic in time and memory to compute a table for number of partitions of n that obey A mod Bi. But even the algorithm we have right now runs pretty fast, so computing 50 terms is not much longer than computing just 30 terms. Okay. So now on to the second part of our talk, searching for partition identities. So how we use this generalized algorithm. So I let you just take a look at this very incomplete list or history of searching for identities. We mentioned the first Rogers-Ramanujan identities, first published in 1894. And McMahon verified by hand, calculating 89 terms. In the year 1952, Lucy Slater worked out a list of 130 Rogers-Ramanujan type identities deduced from Bailey pairs. Bailey was her advisor, and so she worked out more Bailey pairs, and then worked out a list of 130 Rogers-Ramanujan type identities. Many of them are already new, but many of them were new at that time. So in 1970, George Andrews conducted the computer search. 1988, Caporelli conjectured some Caporelli identities from VOA, which stands for vertex operator algebra, and which is proved by Andrews and many others later. In the year 2009, these people conducted another computer search. 2014, Kennedy Russell started their computer search and still ongoing. 2014, same year, Nandy conjectured some conjectures from the algebra, and 3 of these conjectures are still open. So you can see this, get a sense of computer search has been around for a while. And again, this is a very incomplete list. And some of them are found, using Lie algebra. Some of them are found, who knows how Rogers-Ramanujan first found it? It's just like something appeared in his mind and he found these identities. Okay. Before we go on, let's talk about some preliminaries. We call SUMSIDE a generating function that counts the pattern avoiding partitions that we are currently interested in according to these restrictions A mod and I. So this generating function may or may not have an analytic sum or multi-sum. We still would like to call them SUMSIDE. And the product side is a side with infinite products. So we use Frank Gardner's Q-series package to factor the generating function we get from the SUMSIDE, which we obtain from our generalized algorithm. And we factor these generating functions into infinite products. So we use the list notation to denote the product side. For example, -2, -1, 0, 1, 0 denotes this infinite product. So remember, this is a Q-Pocket symbol. So there are 5 things in this list. So that corresponds to, we're considering mod 5, or equivalently, so after the semicolon, we have Q to the 5 everywhere. And so the minus signs correspond to things in the denominator, positive things are in the numerator. And this -2 corresponds to the first, so Q to the 5 to the 7. So 2 corresponds to power, and so why do we have a Q before this semicolon? Because -2 is the first entry in this list. So Q to the 2, Q to the 5, that corresponds to -1, because -1 is the second entry in the list. Okay, so mostly we are interested in list notation that containing entries -2, -1, and 1 for the product side to be interesting. I won't go into that, but this is what we search for, look for in the product side. But so if the list has only -1 and 0 in it, that means the product side satisfies certain congruence conditions. So that's even nicer. For example, -1, 0, 0, -1, 0 denotes this infinite product, which is the parts are 1/4 mod 5, which is famous register management product side. So another notation, MK, that's a set of patterns of length and most M. That is at most M parts and largest part and most K. So say comp 1, 3. Set of patterns of length and most 1 and largest part and most K. So comp 1, 3 is this set. Comp 3, 1 or 2, 2. So you can have 0, 2, 1, 1, and so on. So actually 3 to the second, 9 things here. All right. So this is our search strategy, current search strategy. We used our generalized algorithm GP to obtain GXN sec, which spits out the first n terms of sequence enumerating partitions obeying restrictions according to A mod B and I. And then we program search procedure, which searches partition identities that have product side up to mod n/2. Okay, so why do we have A bar here instead of A? So A bar, you can think of it as a set of A's. So many times we take it to be a power set, but many times we do not. So it's a set of sets of forbidden patterns. For example, A bar can be equal to a set containing these two sets. So we will search through all sets in A bar, power sets of mod. So in quotation mark, because we're actually searching for partition product of the set, the power sets of the sets in mod. So I will use some examples to explain later, as well as power sets of initial conditions. So this S is the set of elements allowed to appear in the list notation of the product side. So again, we we only allow -2, -1, 0, and 1 to appear. And we usually just assume beginning restrictions to be empty set, since we are not too worried about beginning restrictions right now. Okay, so some examples. Let's look at how search works. So a bar, let's say the input a bar is set containing these two sets, mod is empty, I is empty. This means we are searching partitions, either avoid 0 or globally, or avoid 1, 2 globally. So just search through these two elements. So if a bar is empty set, mod is list containing these two sets, I is a set containing this single partition. This means we are searching for partitions that void nothing globally, but either. So there are 4 possibilities for mod because we're taking partition products of the power sets of the sets in mod. So this is how we searched. Okay, so in addition, we are either avoiding 1 as a part or nothing for initial conditions because we take power sets of I. Okay, so this is an opportunity for a commercial break. So this is Emerald. So thanks to Emerald, we are able to split our job into smaller tasks and feed the tasks to 500 nodes and theoretically increase our speed by 500 times. So in reality, some nodes failed, and since we don't own the nodes, the owner can stop the nodes. So, but that happened rarely. But like some of our tasks failed. Still, it's a huge improvement. Okay, so our search space. So I will just use examples to illustrate. So we mainly search for 5 classes. So this is 1, 2, 3, 4, 5 classes of restrictions. So for the first one, a bar is power set of comp to 2. So that means the forbidden patterns must have part less than equal to 2 parts less than equal to 2. Mod is this guy, and it's just less than equal to 1 part, parts less than equal to 3. So one possibility that falls into this class is this. So for the second one, comp 5, 1, 5. So this 5 means we are forbidding at most 5 global patterns. So see here we have, wait, I'm missing something. So we also have 2 European. So here we have 5 patterns in this global in A, but here we are only allowing 5 patterns. Okay, so that's the second search space. All right, so any questions about that? All right, so basically we have to ensure we are checking approximately at most 2 to the 27 sum sites for Emerald to be able to handle in one day. So as mentioned before, we did not exhaust everything in this list because some tasks ran into problems. Okay, needless to say, we discovered many old identities like Gordon, Andrews Pursuit, Caporelli, among many others. But many of them are new or seem to be new. So the way we test whether they are new is we put the corresponding sequence into OEIS, we look in literature, and we ask people. So here I will present a very incomplete list. So the order goes from A mod I to the product side. Okay, so just have you look at them. Okay, so observe that we all actually have mod 12 here. Nothing smaller, because the smaller ones are more likely to yield. So mostly we search for bigger than mod 12. So some more. Okay, so, and from 9 we obtained its companion identity by hand. So notice the global restriction is just this one flipped. So 1, 0 becomes 0, 1. So we, based on experience, played around with the product side, and then flipped this global condition and came up with this initial condition by hand. Okay, so probably the most exciting identity that we found so far is 10. So this is avoiding 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1 globally and nothing else. So observe that the sum side of 10 is equivalent to allowing at most 3 occurrences of every part, because we have 0, 0, 0 here. And for all I not allowed to have I plus 1, I plus 2 appearing in the partition at the same time. So they don't have to be consecutive, but they just don't get to appear at the same time. So that comes from the remaining, so 1, 1, 1, 0, 1, 1, 0, 0, 1, and also this one. So yeah, actually I won't go through that, but just trust me that that's it. And this seems to generalize to an infinite family. So at most k occurrences of any given part, and for all I not allowed to have this k consecutive integers all appear in the partition. Right. Okay, so additional identities. The product sides of 1 through 10 all correspond to partitions whose parts satisfy certain congruence conditions. Or equally, we only allow 0 and minus 1 in the least notation. So here are some identities we found that also allow 1 in the least notation. So that corresponds to having something in the numerator in the infinite product. Okay, this one is interesting because it's 20. So for most of the search, we did only up to n is equal to 30. So we only searched mostly up to mod 15. So this is ongoing research, and we are going to search, hopefully find many more identities like mod 24, so on. So future work. We would like to deal with the cases that are in problems on Emerald. This will enable us to say something like, we have searched everything in this group, and we are sure no identities less than certain modulo can be found in this group. Alright, so that would be nice. And the second one, search for larger modulo identities by increasing the n. Third, put more variations on the initial conditions. And for currently, our approach only deal with conditions on contiguous subpartitions. It would be nice to develop a general framework to search for identities that avoid subpartitions that are not necessarily contiguous. Like in the infinite family we presented, or consecutive. So I actually was at a conference in Florida 10 days ago, talking about similar stuff. And Drew Sales and Ali, I don't know how to pronounce his name. Anyone? Okay, so Drew and Ali offered me some suggestions. So first suggestion from Drew. So some identity have weird sum side. For example, the big gonads companion identity sum side requires difference at least 6 between parts, except that it's okay to have smallest part, 2 parts are 1 and 6. So before, in our algorithm, the beginning restriction and the initial condition are additional restrictions in addition to the global restrictions. But here, actually, we we want to like release, we want to allow certain conditions, right? So we have a global condition, but we also want to allow more things based on the initial conditions. And the second one, incorporate Nandy's asterisk operator, which is asterisk in the pattern 3 to asterisk 3 0 into your program to search for more Nandy type partition identities. So this means we allow any number of 2. So maybe our global pattern could be 3 3 0, 3 2 3 0. Originally, when Eddie asked me this question during the Q&A session, I was a bit stressful, and I said, this cannot be incorporated, but no, this can be incorporated because, even though this looks like an infinite set, right? But we are only in searching for partitions of integer, up to 30 or 50. So this set is going to be finite. So we can certainly incorporate this into our program. And hopefully we'll find more Nandy type partition identities. All right, thank you.
Questions?
Yes, Yoda.
So I think you said that the list notation, sometimes you can think of it as being like congruence conditions.
Yes.
And I was wondering if, for the cases when you can't think of it as being exactly congruence conditions, is there some similar like concrete interpretation that you can give to it?
I was actually puzzled by the same question earlier. So, for example, this 2 here. So Q to the power 2 here. So this corresponds to 2 color partitions, or like if I have 3 here, I have 3 colors, so multi-color partitions. So that's these powers correspond to. So, and this the top one is it doesn't have a strict or direct interpretation, but we can possibly like cancel things out and get meaningful things. Yeah.
Any other questions?
So how quickly does the general algorithm run now?
Okay, so it runs, I think, I remember it's 1,000 some sites and 10 seconds.
Is that per node?
So just on my computer, yes. So.
But I guess that's like for certain values of the parameters. So like, what if you make the parameters like really big, or something like that?
Oh, you're right. Mm-hmm. So this is for 30. So n equals to 30. Yeah. So 50 in my computer, I think it's just like 4 times as long. So it's not too bad.
So in conjunction for the complexity, time complexity.
Yeah. So like I was saying that, I think it can be even made quadratic in time memory. So right now, it's not, but
If it's not already quadratic, how do you think you could make it quadratic?
so it's the same idea. So just do substitution and subtraction. So n minus 1 and minus 1. Yeah.
Oh, yeah.
Right. Since A mod bi and all finite sets.
Well, let's thank Mingjia again.